We're going to look at the Bohr model of the atom, which was proposed by Niels Bohr in 1913. At this point, the Rutherford model of the atom was the accepted model. However, there were a few things that the Rutherford model could not explain. It couldn't explain why electrons remained in stable orbits, why didn't they spiral into the nucleus and lose all their energy. It also couldn't explain the emission and absorption spectra of different atoms, and in particular the hydrogen emission and absorption spectrum. So Bohr's model was able to address these shortcomings. It could explain why electrons remained in stable orbits, and it was also remarkably good at predicting the spectral lines for hydrogen. So Bohr's model was based on some completely unjustified assumptions. So there was two of these assumptions. The first is that electrons orbit the hydrogen nucleus. Well, each atom has one electron. So this one electron orbits the hydrogen nucleus in a circular orbit, much like a planet orbits the sun. The second assumption was that the magnitude of the angular momentum, which has the symbol L, is quantized, and it can only have certain specific values. And these values are given by L is equal to nh bar, where h bar is, just remember, Planck's constant divided by 2 pi, and n is an integer, so 1, 2, 3, etc. So just to recap, the angular momentum vector is given by r cross p, where r is the displacement of the particle, so that's the distance from the origin in a direction from the origin to where the particle is, and p is the momentum. So angular momentum is the rotational version of momentum, much like the torque is the rotational version of the force. So it turns out that these assumptions are in fact completely incorrect. But using these assumptions, Bohr was able to come up with remarkably good predictions of the hydrogen spectrum. So let's work through how Bohr was able to do this based off these assumptions now. So according to Bohr's postulates, we've got an electron orbiting a nucleus. So the nucleus here has a positive charge and is just a proton. So it's got a positive charge plus E. And then we've got this electron orbiting around, and it's at some radius r. And because it's undergoing circular motion, we know that F is equal to ma. And in this case, it's centripetal acceleration. So we've got mv squared on r. Now, the thing which is causing this force is the electrostatic attraction between the nucleus and the electron. So from electromagnetism, we know that Coulomb's law holds, and that force is given by 1 over 4 pi epsilon naught, Q1, Q2, which in this case, both of these charges have magnitude E, so this is E squared over R squared. And in this case, it's an attractive force. So the centripetal force is inwards, and the electrostatic force is also inwards. They're in the same direction. So we can set these two things equal to each other, because this is the resultant force, which is due to this one. So we have mv squared on R is equal to 1 over 4 pi epsilon naught E squared over R squared. So that's what we get from the first postulate. Now, the second postulate tells us about the angular momentum. So we know the angular momentum is equal to r cross p. And in this case, it's traveling in a circular orbit. So the r is in a direction this way, directly towards the particle. And p, that's the direction of the momentum. So that's always at a tangent to the circle. So the radius and the tangent to the circle are always at right angles. So this is just equal to r times the momentum, which is given by the mass times the velocity. So this is the angular momentum, and then Bohr's second postulate tells us that this is equal to nh bar, where n is equal to 1, 2, 3, etc. So we can rearrange this, and we have the velocity is equal to nh bar over rm. Okay, now what we're going to do is we're going to substitute this in here. So let's just simplify this a little bit so we can cancel out that r with one of these r's here. So we have mv squared is equal to 1 over 4 pi epsilon naught e squared on r, and then what we're going to do is replace this v squared with this. So we've got m times n over h bar over rm squared is equal to 1 over 4 pi epsilon naught e squared on r. So expanding these brackets, and what we'll do is h bar is equal to h over 2 pi. We'll actually replace the h bar with the h because we've got a 4 pi here, so then we'll end up with some cancellation. So we have m times n squared times h bar squared, which is equal to h squared over 4 pi squared. So these combined are h bar squared, and then we've got an r squared, m squared, and this is equal to 1 over 4 pi epsilon naught e squared on r. Okay, now what we're going to do is rearrange this for an expression for r, but before we do that, let's cancel out as much as we can. So we've got an m on the top and an m squared on the bottom, so that square cancels out. We've got 4 pi squared here and 4 pi here, so we're just left with a pi on this side. We have an r squared here and an r here, so one r will cancel with one r. And so rearranging this and making r the subject, we've got r is equal to, well, what was left on this side inverted. So we've got epsilon naught over e squared and then times this. So we've got n squared h squared over pi m. So the radius is equal to epsilon naught h squared over e squared pi m times n squared. So we have different orbitals corresponding to these different n's that are allowed. So we'll call our first orbital R1. We'll give it a special symbol A, and this is known as the Bohr radius, and this is equal to the radius when n is equal to 1. So this is equal to epsilon naught h squared over e squared times pi m. And then we'll have other radii which scale as this n squared here. So we can write r is equal to a, which is this thing, times n squared. Now we can calculate what a is if we want. We've got 8.854 times 10 to the minus 12 times h squared, which is 6.626 times 10 to the minus 34, and that's squared over e squared, that's the charge on the electron, 1.602 times 10 to the minus 19 squared times pi times the mass of the electron, 9.109 times 10 to the minus 31. Solving this, we end up with 5.292 times 10 to the minus 11 meters, or we can write it as 52.92 picometers. So this gives us the radius of the smallest orbit. And this is how Bohr's model of the atom tells us that the electron cannot spiral into the nucleus, because this is the smallest radius that the electron can have. There's no allowed levels closer to the nucleus, so the electron can only be in allowed levels and can't be closer to the nucleus than this. Now we can take Bohr's model a bit further and we can consider the energy levels of these different orbitals, and from that we'll be able to predict the spectrums. So we know that the energy of the electron is equal to the kinetic energy plus the potential energy, and the kinetic energy, that's given by a half mv squared. The potential, in this case the force that we're considering is the Coulomb force, the electrostatic force. So you learnt in electrostatics that the potential U is equal to 1 over 4 pi epsilon naught times Q1 Q2 on R. So that's the potential in this case. So we've got plus 1 over 4 pi epsilon naught in this case, these charges are equal and opposite. So we end up with minus E squared over R. Now what we can do is substitute in for V squared, because we found an expression for mv squared up here. So all we're going to do is substitute that in for this mv squared here. So when we do that, we end up with a half times 1 over 4 pi epsilon naught E squared on R. And then here we've got minus 1 over 4 pi epsilon naught E squared on R. So we've basically got an eighth 1 over pi epsilon naught E squared on R minus a quarter pi over epsilon naught E squared on R. So this gives us minus an eighth over pi epsilon naught E squared on R. Now we have an expression for what R is. R is equal to AN squared, where A is given by this. So what we can do now is substitute into this to get the energy of the nth level. So we've got minus 1 over 8 pi epsilon naught E squared, and now we're substituting in for R, and R is equal to epsilon naught H squared, and then divide by, so that goes up the top, E squared pi M, and then that's for R1, but R is A times N squared, so that N squared ends up on the bottom. Okay, so let's do some simplification. These pi's will cancel out, and so we end up with this is equal to minus m e to the 4, that's everything that's left on the top, divided by 8. Now there's 2 epsilon naught, so epsilon naught squared h squared times 1 on n squared. So this gives us an expression for the energy levels. So what I'm going to do now is clear the screen, and then we'll look at the energy levels in a little more detail. Okay, so up here I've written our energy expression that we just derived, and here I've pasted a copy of our hydrogen emission spectrum. So this red line here is at 656 nanometers, and I've tried to write the wavelengths of the other lines down here. Okay, so let's start by calculating the energy of the ground state. So the ground state is the energy with n equals 1, and so that's going to be equal to minus m e to the 4 over 8 epsilon naught h squared, epsilon naught squared, sorry, times 1 on 1 squared, so times 1. And substituting in, this is the mass of an electron, so this is equal to 9.109 times 10 to the minus 31 times the charge on an electron, 1.602 times 10 to the minus 19 to the power of 4, divided by 8 times epsilon naught squared, which is equal to 8.854 times 10 to the minus 12 squared times h squared, 6.626 times 10 to the minus 34 squared. So you can enter all that into your calculator. You might need to be a bit careful of the way in which you enter it, because you have some fairly, well, very small numbers here, large negative powers. And so when you do that, you end up with minus 2.1789 times 10 to the minus 18 joules, which will convert to electron volts, and we end up with minus 13.6 electron volts. So that's the energy of the ground state. Now we can calculate the energy of other states as well. The energy of the n equals 2 state is just going to be equal to m e to the 4 8 epsilon naught squared h squared over 1 on 2 squared. So it'll actually be a quarter of this thing. So it'll be a quarter times E1. And so that's equal to a quarter of this, which is equal to minus 3.40 electron volts. E3, this is going to be 1 over 3 squared times this thing. So it'll be actually a ninth of E1. And so that is equal to minus 1.51 electron volts. And then let's do one more, E4, which will again be a 16th 1 on 4 squared times E1, which is equal to minus 0.85 electron volts. So what we can do is draw a little energy diagram over here. Here's E1, which is 13.6 minus 13.6 electron volts. E2, which is equal to minus 3.40 electron volts. Then we've got E3, which is equal to minus 1.51 electron volts. And finally, here's E4, which is equal to minus 0.85 electron volts. And we've discussed before when we were looking at the Schrödinger equation how when electrons transition from one energy level to another, that's when they release a photon. So if we go from E2 to E1, we're going to release a photon, and that's going to have an energy, delta E, which will be equal to E1 minus E2, which will be equal to HF. So we can actually calculate the wavelength of this photon released in this transition here. And we have that the energy when it goes from 2 to 1 is going to equal HF, which will be HC on lambda. And so this tells us that the wavelength is going to be equal to HC on E from 2 to 1. And so this will be equal to 6.626 times 10 to the minus 34 times 3 times 10 to the 8 divided by this energy difference. So the energy difference between these two states is the 13.6 minus 3.40, and that's in electron volts. So to get this into meters, we need to convert this to joules. So we times it by 1.602 times 10 to the minus 19. And when we solve that, we end up with 121.6 nanometers. Okay, so this is a short wavelength, an ultraviolet wavelength, so we don't see that on the spectrum here, but it is possible to measure for this with the right sensor. And in fact, we do find this wavelength in the emission spectrum of hydrogen when we're looking at the right wavelengths. So in fact, when electrons transition from higher energy states down to lower energy, to the ground state, these are known as Lyman lines, and we can calculate the wavelength of all the different Lyman lines using, instead of E2, we'd use E3, we'd use E4, etc. And there is good agreement between the calculations and the actual experimental measurements. Okay, but we haven't worked out how we get these lines. So these lines actually turn out being in the Balmer series, which is when electrons transition to the E equals 2 level. So one of these is going from E3 to E2. So let's calculate the wavelength of that line now. So to calculate the wavelength of this first Balmer line going from E3 to E2, once again we'll have HC over, in this case it's E3 to E2. And so again we just substitute in 6.626 times 10 to the minus 34 times 3 times 10 to the 8 over the energy difference here. So we've got 3.40 minus 1.51 times 1.602 times 10 to the minus 19. And solving this one, we end up with 656 nanometers. And that is exactly what was observed in this hydrogen emission spectrum here. So this is the first Balmer line. As it's the smallest frequency transition to the E equals 2 state, the first excited state. And then just to check that isn't a fluke, let's calculate the next one. So the next line in the Balmer series is when we drop down from the E equals 4 level. So these aren't color-coded in any sensible way, but we're now going from E equals 4 to E equals 2. That's what this one is. And so once again, 6.626 times 10 to the minus 34 times 3 times 10 to the 8, and divide by the energy difference in this case, which is, we're going to the equals 2 still, so it's still 3.40, but in this case it's from the 0.85 level, so times 1.602. And when we put all, times 10 to the minus 19, and when we put all that into the calculator, we end up with 486 nanometers, which is this second line here. So this is showing that Bohr's model of the atom gave very accurate predictions for where the lines in the hydrogen emission spectrum should be. While the Bohr model's good at predicting the absorption and emission spectra for hydrogen, it in fact fails for every other element. The reason for this is that those assumptions that it's based on are completely incorrect. So it turns out to be purely a coincidence that it was so great at making the predictions for hydrogen.